Okay, good morning, everybody. Let's start with a riddle this morning. Why don't plants have brains? Why don't plants have brains? That we know of. They don't need them because why don't they need them? It rains, okay. It's part of the answer.
Don't have room for it?
Maybe. I don't know. There's some pretty big plants out there. Bigger than us.
They aren't like mobile.
They aren't mobile. So we are going to finish lecture 10 today, and we're going to move on to a two-part lecture on really the fundamentals of robotics, which we've been kind of putting off for a while now, which is the problem of how to get from point A to point B. So animals have hit on one general strategy about how to survive and thrive in this world, which is instead of waiting for the rain, the mate, the food to come to us, we go to it. Plants have adopted the complementary strategy, which is cross your fingers and hope that the resources you want will eventually come to you. So what are brains for? There is no simple answer to that, but what brains were originally for was to orchestrate movement. Everything else that brains do, including human brains, are a hack or a series of hacks on top of that. So we're going to talk about the origins of locomotion and really dig into the challenges about why moving from point A to point B is so challenging, and how, once you start to solve that problem of self-displacement, moving yourself from point A to point B, it provides the foundation on which all the other building blocks of intelligence can be built upon. Okay, a little preview of where we're heading. Back to logistics for a moment. We will finish lecture 10 in a moment, and then we will move on to lecture 11, legged locomotion. Today, undergrads, you are moving on to assignment 7. Hopefully, most of you successfully wrestled with refactoring your code, more or less. I know through office hours that some of you are struggling a little bit. Hold tight, don't stress. Assignment 7 is coming, and assignment 8 will be assigned next week, but then you've got a little bit of breathing room for the spring recess. So if you are starting to fall behind, you're going to have a little bit of breathing room to catch up in 2 weeks' time.
When it comes to the refactoring, how important is it that we're like exactly on your intent of how we refactored it versus just like being aware of how it works for us?
Absolutely. So if I may summarize your question, do you need to follow the letter of the law or the spirit of the law? The answer is the latter. You do not necessarily need to follow exactly what I'm asking for in refactoring. The spirit, of course, is for you to try and clean up and modularize your code so you understand it better, right? For most of you, I'm going to guess that at this point your code base is getting large enough that you're starting to forget where this variable is, where is motor values, where are the synapses, how do I update them. That is part of the reason for this refactoring and cleaning things up. So your code base is more clean, more structured. It's easier for you to dive back into it and find what you need at a moment's notice in order to push on through 7, 8, 9, and 10, and ultimately your final project. For you to be successful in your final project and be able to quickly identify all the parts of the evolutionary algorithm and improve that, or quickly identify all the parts of the neural controller for your robot and improve that, you need to have a clean, modularized code base. Make sense? That being said, within constraints, so that you can show us what we want to see at the end of assignment 6. All good? Okay, those taking the course for graduate study, the second differentiable assignment is now available, in which you're going to be adding springs to connect together the mass points that you created in the differentiable assignment 1. grad students that have made it this far, you realize obviously that you're doing D1 through D5 in Colab, which is a browser-based programming environment, in order to clear the level the playing ground for everyone, so we don't have all the installation issues we had with Ludobots. Everybody is using exactly the same resources, which is Google's resources. Yeah. The other reason we're doing everything in Colab is so that you can access the GPU resources that that Google makes available through Colab. You don't necessarily need those GPU resources yet because we're not really doing any heavy optimization in Colab yet. However, some of the grad students, there are little prompts, especially in D2, that challenge you to actually start to do some differentiable optimization of your robot in its current state. Be careful. If you do too much compute within Colab, you can get bumped off by Google for a day or a week or possibly longer. So for those of you that are coding stuff up in Colab, go lightly for now. When you get to D5, when you're really going to do some differentiable optimization or some differentiable design of your robot, we'll see how things stand at that point. If you're able to run the code base if you're able to run your code base outside of Colab on your own machine using GPU resources, that's fine too. For now, just be careful. Any other questions, things that have cropped up with the differentiable assignments? I know that one student was struggling with actually viewing the movie or viewing her simulation in the Colab window. Has anybody else had this problem? Have you managed to solve it yet?
I just did what you said, download it and put it in the VCL or player.
Okay, all right. So it's not an ideal solution, but for now, if you can't see the simulation in Colab, you're going to have to download it every time you make a change to the code, which is a little annoying. So at some point, you may want to just wean yourself off Colab and run it locally. We'll see. I'll keep working on a solution to that. Any other questions about any of the assignments? No? Okay. Looking ahead to next week, I am going to be traveling to a workshop in the UK, so there will be no in-class instruction on Tuesday and Thursday. Do not come to class next Tuesday and next Thursday. I will record next Tuesdays and Thursdays lectures, and I will drop them into these cells at the time we usually meet. So hopefully for you, there's not much of a disruption to the way you are currently absorbing this course. When I travel and we miss class, I make it up to you by bringing back something good to eat from the country that I'm going to, which in this case is the UK. So I will hold on to what I bring back for you. Be sure to be here in class the Tuesday after spring recess, and I will make it worth your while. Fair deal?
Does that mean you do or don't have office hours on that Monday?
Good question. It's a 5-hour difference, so I don't know whether I will be able to host live office hours.
You won't be here.
I won't be here. If they're office hours, they will be remote. I would say probably to be on the safe side, if you want me the first week of March here, send me an email and let me know, and we can either do things through email or set up a one-on-one Zoom meeting. I think that's probably better than trying to orchestrate office hours. Make sense? Fair? Okay. All right. So where were we? We were working our way through some of the initial experiments in the field of evolutionary robotics, and we are finishing with this last one, which is really not very much of a minimal cognition experiment. We've got a not minimally complex neural controller of this robot. It's a relatively complicated neural controller, and the body of the robot itself is also anthropomorphic. There's a lot going on in terms of body and brain. We ended last time by focusing in on the 47th and 48th neuron inside this 48 neuron CTRN that's controlling this robot. And we were looking at the ways in which the investigators in this experiment extracted signals from these two neurons and interpreted that extracted signal as the robot telling the investigators whether the robot thinks it's in contact with the sphere or whether it's in contact with an ellipsoid. There's some simple ways we could do it. If the value of 47 is greater than the value of 48, that's the robot telling us it thinks it's in contact with the sphere. If 48 is firing more strongly than 47, that's the robot telling us it thinks it's in contact with the ellipsoid. That's not what the investigators did. What the investigators did was something more complicated than that, which was to watch the values of neuron 47 and the value of neuron 48 during the last 5% of the time steps of the simulation. Remember that in a phase diagram, in a 2D phase diagram like we have here, we're watching two values, 47 and 48, and we're looking at what their values are at a given point in time. Then we're looking at a given point in time, then we're looking at what their values are at the next point in time, next point in time, next point in time. And what we get is a trajectory that crawls through this two-dimensional space and reports out how these two values are changing during the last 5% of the robot interacting with whatever object we placed in front of it. So far, so good? Okay. The first thing that the investigators do at the end of a simulation is draw a bounding box around a trajectory that was produced when the robot was in contact with the sphere. Remember, the investigators know, but the robot doesn't know, or we don't know whether the robot knows. So in this case, the investigators have placed a sphere S underneath the robot's hand during the EF trial. So we're going to draw a rectangle R around the trajectory produced when the robot was in contact with the sphere during the EF trial. Again, I'm not a big fan of this notation, but this is what they used, so we'll go with it. So we've got R sub S sub E, the R representing a rectangle. So far, so good? Okay, they take the same CTRN, drop it back inside the robot after resetting the robot, and now they place an ellipsoid underneath the robot's palm, and the CTRN starts firing. Sensor values flow to motor neurons. The robot starts moving and manipulating this ellipsoid. And again, the investigators watch, in this case, what the trajectory of neurons 47 and 48 do when the robot is in the presence of an ellipsoid during the ETH trial, or the ETH plus 1th trial. So far, so good? Question?
So the phase diagram, is that, so that arc, is that the activation of the neuron?
It's the activation of the neurons, yeah? So here's our visual representation, or our geometric representation of what's going on. Here's the mathematical representation of exactly the same thing. Question?
Is there a reason you don't start at 0? Or is that just...
Yeah, so let's start at 0. So during the first time step of the simulation, we place the robot's hand on top of the object. We set all the values of the output neurons to 0. And you're right, we actually do start at 0, 0. The robot starts doing something during the first 95% of the time steps of the simulation. And then this is what happens during the last 5% of the simulation. Good point. I just wasn't drawing that part. And same thing here, right? For the ellipsoid, the robots, these two values start at 0, 0, and maybe for a while the robot is doing the same thing, and then eventually this happens.
You might have already mentioned this, but is that last 5% like in orbit? Or like is the last 5% the same as the 5% that would happen after?
Good question. So does this pattern repeat itself? Who knows? It depends on all of the settings of the CTRN. We're just describing a hypothetical situation with one CTRN, which in our example, we've only evaluated that CTRN twice. Once on the robot in the presence of the sphere, and a second time with the robot in the presence of an ellipsoid. Maybe it would draw a cyclical pattern. Maybe it would repeat itself. Maybe the robot rocks its hand back and forth over the top of the object. in which case 47 and 48 might oscillate back and forth. Maybe the robot, I'll draw it over here, maybe the robot rocks its hands back and forth and comes to a stop over the object. Maybe the object, or maybe the robot just is randomly manipulating the object and we get some random trajectory. It depends. It depends on the settings of the CTRNN. The investigators are not forcing this. They're just, at this point in the experiment, watching and recording what values of 47 and 48 a given CTRNN produce. So far, so good? Okay. All right, so let's go back to the math for a moment. So they're defining these bounding rectangles, and they're going to define the bottom left vertex of the rectangle as the minimum values of 47 and 48. And they're defining the top right corner or the top right vertex of the bounding box to be whatever the maximum value of 47 was. There's the maximum value of 47. And the maximum value of 48. You'll notice there's a whole bunch of other math sitting inside here. What is that math? Where is that coming from? Hopefully it looks familiar.
Isn't that the activation?
Absolutely, right? So here's our activation function. Here it is sitting in here and here. So you'll remember, hopefully you remember during our discussion about CTRNNs, the value inside a neuron, the raw value can be very large, very positive or very negative. But when we go to read out or extract the value out of a neuron, we pull it through the activation function. We add the bias, we pull it through the activation function, and we get a value back between -1 and 1 or 0 and 1. Doesn't really matter for our purposes. We're squashing that value. Emily.
About the network, are they implying with the lines that it's fully connected and they're just being simple, or is there a more intricate connection?
Yeah, so what is the connectivity pattern inside the CTRNN? Is it fully connected? Most of the CTRNNs we've seen so far, we were wiring up every neuron to every other neuron. Is that the case in this CTRNN? And the answer, actually, you can see it in the visual representation, and if you're paying attention, you can also read it out of the equations.
So they're connected to the internal neurons, fully connected, but not like directly to each other?
Absolutely. So this is not a fully connected network. You can see that for neurons 23 through 30, which is down here, these are all fully connected to themselves, and then they connect out to the motor neurons. None of the motor neurons are connected to any of the sensor neurons, and none of the sensor neurons directly connect to the motor neurons. Why did they make these particular design decisions? Who knows? They don't give their reasons in the paper. Seems kind of arbitrary to me.
Yeah, I was gonna ask, like, when you're designing like the architecture of one of these, like, is the art, like, obviously like the recurrence matters, but generally like you kind of do just make choices arbitrarily and train it, right?
Another dirty secret of AI. The choice of cognitive architecture, how you wire up all the neurons in your neural network, kind of arbitrary. Not completely arbitrary. We've learned a few things over the decades, but it is really difficult to know how to establish the appropriate cognitive architecture. What should be wired up to what to make learning, or in our case, evolution, run more smoothly. Yet another open problem in AI.
I saw a professor saying recently it's more like alchemy than it is like chemistry.
It's more like alchemy than it is like chemistry. Absolutely. Yes, it is somewhat arbitrary. In this particular experiment, not casting any shade on the investigators, I know them quite well. It was kind of an arbitrary choice, I think, in this case. Okay. Some things are known. As was just pointed out, probably good to have recurrent connections in there. For a lot of tasks, it's helpful for the robot to be able to remember things that have occurred in the recent past. Okay. All right, back to our example here, our cartoon example here. At this moment in time, the investigators have recorded the activations of 47 and 48 from a presentation of the sphere and one presentation of the ellipsoid. Remember that for each CTRNN, we're going to evaluate that CTRNN 16 times. We're going to set the robot's initial position to position A, and then expose it to this sphere, put it back to A, this sphere, A, sphere, A, sphere, A, ellipsoid, A, ellipsoid, A, ellipsoid, A, ellipsoid, 8 times. Take the same CTRNN, evaluate it 9 through 16 times, starting the robot's initial position at B, then in position B, expose it to the sphere, reset the arm to B, put the sphere back under, B sphere, B sphere, B ellipsoid, B ellipsoid, B ellipsoid, B ellipsoid. 16 evaluations of an individual CTRNN. So far on the board, I've only drawn 2 of those 16. Let's go back to the second presentation of the sphere. We presented the sphere once to the robot. Now we're going to present the sphere a second time, and we're going to rotate the sphere horizontally under the robot's palm by a small amount. Tell me about what 47 and 48 are going to do in this new case. It's going to do exactly the same thing. And we're going to get a second R sub S sub E that's identical to the first one. Let's skip ahead. Let's imagine that this particular pattern was produced when the ellipsoid at this angle was placed under the robot's palm. We replay the same CTRNN, but now we place the ellipsoid back under the robot's palm and rotate the ellipsoid a little bit. Tell me about how 47 and 48 are going to behave in this case.
It'll just look different.
It'll just look different. I don't know what it's going to look like. Again, it's going to start here and do something for the first 95% of the time, and then do something different during the last 5%. And we're going to put another bounding rectangle around this one, where this rectangle represents another presentation of the ellipsoid under the trial. So far, so good. So at the end, we're going to end up with 16 bounding rectangles. 8 of them are going to be lying more or less right on top of one another, and the other 8 are going to be distributed somewhere in this 2-dimensional phase diagram. Everybody with me so far? Okay, we'll skip ahead a little bit. We'll assume that we've finished all 16 presentations of the objects to this CTRNN. And the last thing we're going to do to finish up the evaluation of this one CTRNN is we're going to place another bounding box around all of the sphere bounding rectangles. So we're going to place a C sub S. Sorry, this is getting a little messy. Hopefully you can do a better job. We're going to place another bounding rectangle called C for these are the things that are classified as the sphere from the robot's perspective. And we're going to place another bounding box around all the R sub Ds. I should have brought a differently colored marker to class today. We're going to put another one here, a big bounding rectangle around all of these, and these correspond to the category of ellipsoid. So far, so good? Okay. We have not yet said anything about the fitness function for this experiment. Verbally, I've told you that the investigators want this robot to be able to distinguish between spheres and ellipsoids. What's the final step, do you think? We need to calculate the fitness function, or the fitness value. We need to obtain one floating point number, which represents how well the robot does at distinguishing between spheres and ellipsoids.
Could you just find a number that classifies what if you're in the last 5% is in the sphere box versus in the non-sphere box?
Well, remember that the sphere box, we're placing that around all of the activations of 47 and 48 when the robot was actually in the presence of the sphere. And we've placed a bounding box around all the activities of 47 and 48 when the robot was in the presence of the ellipsoid. What do we do with C sub S and C sub D to derive a single number?
We compute the area of
The area of?
the rectangle.
We could compute the area of C sub D. We could compute the area of C sub S. And then what do we want to do with those two areas? Those are two numbers.
Yeah, we compare like which one. If they're close together, then more repeatable, I guess. So you have a single number.
If they're close together, we're getting close to the answer now. Other ideas?
Do we want to maximize the difference between them?
Maximize the difference between,
The areas. Or sorry, the centers of them maybe.
maximize the difference between the centers. We're getting closer.
You also want to minimize the area of the box.
Maybe minimize the area of the box. So if we want to maximize the distance between the centers, you can imagine two massive C's, C sub S and C sub D. Imagine these are huge. So these two distances are also pretty huge.
I was just going to say, we also want to have them be, like, the distance needs to be on a certain axis, right? Because if we were just maximizing the distance, you could have the categories be, like, totally flipped.
Maybe. Other ideas?
Like max or minimize the overlap.
That's it. Minimize overlap. We want the robot to have maximally different felt experiences when it's in the presence of these two different objects. Everybody got everything inside here? I'm going to erase it. Okay. That's the key to this whole complicated, long experiment, is to minimize the overlap between these bounding boxes. What we want, ideally, is whenever the robot experiences the sphere, it does something like this, and whenever it experiences the ellipsoid, it does stuff like this. Remember that both sets of trajectories are starting from here. We want the robot to diverge its experiences. We've heard that idea before. We're placing the robot in the presence of two different objects, and we're creating a fitness function that is selecting for or rewarding for increasingly felt differences from the robot's perspective. Where have we heard this before? We heard this last class. We're trying to evolve the robot to actively, categorically perceive its world. And one way to do that is to reach out in the world and say, I don't know, is this piece of fruit, is this food, or is this poison? I remember that if it's this color and it feels like this, that's actually a bad thing. I can't quite tell, so let's reach out in the world and do stuff to magnify the difference between categories. That's what this fitness function is going to select for, to minimize the overlap between these bounding boxes. In this cartoon example on the board at the moment, there is 0 overlap.
So where is the fact that the bounding boxes are differentiating between ellipsoids and spheres from versus just like differences that these neurons are creating between the objects?
That's it. 47 and 48 behave differently. They report similar, the fitness function is going to select for the 47 and 48 to behave similarly when in the presence of the sphere, and behave similarly in the presence of ellipsoids, regardless of how the ellipsoid is placed under the palm of the robot. And 47 and 48 should behave very differently when it's in the presence of these different objects. Yeah? Okay. let's assume we've done evolution and we actually have evolved a C tier and N that causes the robot to do this exact thing. And now we take the ellipsoid again and we put it back under the palm of the robot, but we rotate the ellipsoid or we place it at some particular horizontal position under the palm of the robot that robot or that C tier and N never saw during evolution. How do we know whether the robot knows that it's in the presence of an ellipsoid?
We would have had to store like the bounding boxes from before, right? To decide if it is like whatever trajectory it traces is in either one of them.
Exactly, right? So for that evolved C tier and N, we have C sub S and C sub D. We know that for the C tier and N. If we place an ellipsoid under the robot's palm in a new configuration and 47 and 48 do this, that's the robot telling us this is an ellipsoid. If we place an ellipsoid under the robot's palm and 47 and 48 do this, that's the robot telling us I'm in the presence of a sphere. The robot is wrong in that case.
What if it takes a trajectory that's like not in one of your bounding boxes?
What if we place the ellipsoid under the palm and it does something like this? What is the robot telling us?
It doesn't know.
I saw a bunch of you do this. Exactly. The robot says, I don't know. That's it. Okay. All right, that's the intuition. Let's look at the actual fitness function, FF. Again, terrible notation here. FF is a single variable. They're going to set the fitness function to be the sum of two different terms. F1 and F2 are just sitting here by themselves. There's no negative signs in front of them. They're not on the denominator. So whatever F1 and F2 are, F1 and F2 should be maximized. An optimal robot gets very positive values of F1 and positive values of F2. Let's actually start with F sub 2 because we were just talking about F sub 2. If you look at F sub 2, inside you'll notice there's an intersection sign. And this is exactly the point that Eric was pointing out here, is that we are trying to minimize. This intersection is on the right-hand side of a minus sign. We are trying to minimize the area of the overlap between C sub S and C sub D. We're trying to minimize this area. This is C sub D and this is C sub S. What's going on in the denominator? Why is there a denominator?
You're like normalizing over the biggest or the smallest area of the bounding box.
Yep, absolutely, right? So this, you can imagine a perverse instantiation case where this is C sub D and this is C sub S. C sub S is really small. There's actually quite a bit of overlap between these two boxes. The robot actually can't tell the difference very well between C sub S and C sub D in this case. So this denominator is guarding against this particular case of a perverse instantiation. And the fact that it's there is usually a pretty strong hint that the investigators probably ran this experiment without this denominator to start with and probably got something like this and then said, oh yeah, right, okay. Normalize by the smallest of the two bounding boxes.
So does that have the effect of trying to also like maximize the area of the two?
Does this fitness function also exert evolutionary pressure to maximize the size of the boxes? Great question. Thoughts? I don't think so, but it's a good question. I'm not 100% sure. It might be something to run and see.
So if they wanted to, could they have like created a machine learning algorithm to kind of create like a line separating the boundaries and then like to not have it be like it doesn't really know, it'll just intuitively be like, it's more on this side, so it's going to be an ellipsoid, versus it's more over here, so I'll say it's a sphere.
They could have. There's an infinite number of ways they could have done this, right? So your suggestion is interesting. We force it to just draw a line and distinguish. You're forcing the robot then into making one of two choices. It has to say, I think it's the sphere, it's on this side of the line, or it's on this side of the ellipsoid. I like this solution because there's actually three options available to the robot. The robot can say, I think it's an ellipsoid, I think it's a sphere, or I don't know. Okay, you notice that f sub 2 is a conditional, so the robot gets, or the CTRNN gets fitness points if f sub 1 is greater than or equal to 1. If f sub 1, which we haven't talked about yet, is less than 1, the robot isn't able to get this. F sub 1 is dinner, and f sub 2 is the dessert. You don't get your dessert if you don't finish your dinner. This particular fitness function is an incremental fitness function. We've seen this before when we saw the gantry robot. This fitness function is set up so that evolution will evolve CTRNNs that do very well, get better and better and better at F1. And then when a CTRNN appears in the evolving population of CTRNNs that gets an F1 above 1, then it also starts to collect points for this. Okay, so let's have a look at f sub 1. F sub 1 is a function of d sub e, which is the Euclidean distance between the object and the center of the palm of the robot at the end of the trial. And d sub max is the maximum possible distance the robot's palm can get from the object. What is F1 selecting for?
They want the hand to stay on the object.
This is a very strong hint. Actually, it's a mandatory requirement that CTRNNs control the robot's motors so that the hand stays in contact with the object, because this robot has no cameras. It can't see the object. It's got to feel it in order to know the difference between the objects. Everybody see that? You can imagine that starting from either position A or position B here, 99.99999% of random CTRNNs you create are going to cause the arm to do things like this and maintain very little and temporary contact with the object. It's going to be super hard and take you years to start to evolve a CTRNN that actually can distinguish between the objects. So they're building in some pretty strong intuition that they have about this problem, which is that if you're going to distinguish between objects by touching them, then touch them. Everybody see that? Okay. Okay, here we go. I'm going to turn out the lights for this one. Hopefully you can see this. Maybe I'll try maximizing this. Yeah, that's better. Okay, here we go. You're going to watch, what we're going to watch now is a video of the robot being controlled by one of the most fit CTRNNs. So the evolutionary algorithm has run and has produced a CTRNN that minimizes the overlap between C sub S and C sub D. While you're watching this video, and I'll just put it on continuous loop here, I want you to jump back and forth between watching what the robot actually does and what's going on in the bottom left of the screen. And I apologize about the colors. It's a little hard to see. What is the robot doing? What is the robot, quote unquote, saying?
Trying to roll it straight back, and if it rolls straight back on a straight line, it calls it a sphere. If not, it calls it an ellipsoid.
Okay, so some good observations here. Obviously the robot has, or the CTRNN has hit on a strategy of just rolling the object backwards. And the observation is that if the robot pulls the object back and it rolls back in a more or less straight line, that seems to correspond with the robot saying it's a sphere. Otherwise, it says it's an ellipsoid. Other observations?
It's like curling its fingers back.
It's curling its fingers back a little bit.
Is there actually a difference between the sphere and the ellipsoid?
Is there actually a difference between the sphere and the ellipsoid? You're doing passive categorical perception. You're trying to perceive at a distance the difference between these two objects. It's not easy, is it? They made this hard on the robot. The major and minor axes of the ellipsoid are very similar to one another. This is a very spherical ellipsoid, but yes. These investigators were mean but not diabolical. There actually is a difference. It's just a subtle difference.
My question is that, like, with this strategy, if it rolls it like straight on the minor axis, it wouldn't be able to tell, I don't think.
Okay.
But also the simulation time's like, oh, I guess the fingers help too because it's curling its fingers. Yeah.
Remember, there's a lot going on here. The robot's getting a lot of touch and proprioceptive information in its fingers, its wrist, its elbow, its shoulder. There's tons of subtle differences going on in this video between the case of the sphere and the case of the ellipsoid, some of which you can see, some of which you can barely see, and some of which you can't see. It's a great example of, again, thinking about thinking is misleading. The robot doesn't need to do something crazily different in all cases. From the robot's perspective, these cases feel very differently. They don't look very different to you, presumably. Tell me, I apologize, the blue arrow is hard to see in the bottom left. What's up with the blue arrow? What is the blue arrow? What is it representing?
Classifying.
It's classifying. How? How did they know how to draw the blue arrow during the rendering of this video?
So it's like sitting up until the phase diagram goes into one of the boxes.
So if the value of neurons 47 and 48 at the given time step of a frame in this video, if 47 and 48 are outside a bounding box, that they draw the arrow straight up. If 47 and 48 wander inside to C sub S, the arrow switches and points to S, to sphere. If the trajectory wanders back out and wanders into C sub D, that's the robot saying, I'm in the presence of the ellipsoid.
Do you know if they tested it with like different sizes?
We're going to see some examples of that in a moment. So if you watch the blue arrow is the robot saying to us, I don't know. Oh, it's the sphere. No, wait a second. No, it's the ellipsoid. Yeah, it's the ellipsoid. It's the ellipsoid. It's the ellipsoid. Next presentation. I don't know. Ellipsoid, sphere. It's the sphere. It's not sure, and then it converges most of the time on the right answer. Everybody see that? Okay, this is the best evolved CTRNN, and what you're watching is a video of playing that CTRNN back in initial position A. I'm going to show you exactly the same CTRNN, but now that CTRNN is going to be played multiple times on the robot, starting in position B, not position A. Got it? All right, here we go. What's happening?
It's actually moving its elbow a lot more.
There's something going on with the robot is moving differently, which is not surprisingly. It's in a pretty different pose. How is it doing? How well is it doing?
Worse.
It's worse. This is harder. This is a tough task.
It looks like the wrist is kind of getting stuck. Like it's like kind of getting stuck on the ground, and then it doesn't really know how to keep rolling.
The wrist is getting stuck on the ground and the robot doesn't know how to keep rolling. I love it. Very Valentino Breitenberg-esque language. Maybe that's helping. Maybe that's part of the strategy. Who knows? Who knows? Okay. All right, let's look at some actual data now rather than some video. I'm going to flip the lights back on. Okay, so As usual, here's a plot of evolutionary progress. We have evolutionary time on the horizontal axis. So evolving populations of C tier and Ns to do better and better at minimizing the overlap between C sub S and C sub D. They evolved one population of C tier and Ns for 500 generations, and the video you just saw was the most fit C tier and N from that run. Then they rewound the evolutionary tape, started with a completely different population of random C tier and Ns, evolved it again for 500 generations, and plotted at each moment in evolutionary time the fitness of the best robot, the best C tier and N in the population at that time, rewound the tape, ran it forward, ran evolution again a third time. What happened during these 3 evolutionary trials?
They all kind of plateaued at 2.0.
They all plateaued at 2.0. I'll leave it as optional homework. You can work through these equations. F1 and F2 are designed to range between 0 and 1. So the best the robot can get is 2. The worst it can get is 0. It's doing pretty well. It takes a while, but in all 3 cases, the evolutionary algorithm was able to evolve a C tier and N that correctly categorized all quote-unquote 16 objects. The robot doesn't know that there's not 16. We know. Yeah? So pretty successful, actually. Let's dive into the brain of one of the more successful robots. So among all those 3 trials, this was the best C tier and N. And like we've seen now many times in the minimal cognition experiments, they're going to take that most fit C tier and N and play it back thousands of times on the simulated robot in conditions that the robot didn't see during evolution. You'll notice mentions of 180 rotations. During evolution, they rotated the ellipsoid to 4 different horizontal rotations. They played that C tier and N back in the presence of 180 different horizontal rotations and 180 rotations of the sphere. In scare quotes, because obviously horizontally rotating the sphere makes no difference to the robot. The dashed rectangles that you see are the C sub S, and C sub D. The little rectangles are the R sub S sub E's and the R sub D sub E's. What's going on in this case? What can you tell me about what's going on in the head of this robot during all these experiences?
The spheres seem to be a lot more similar in like the outcome of the robot, whereas the ellipsoids are like a lot more sporadic.
Absolutely, right? So the bounding box for C sub S is smaller than the one for C sub D, which makes sense, right? There's not a lot of difference in rotating the sphere.
So is this like for one trial, is it for like the whole algorithm?
It's for one C tier and N. So they ran the evolutionary algorithm. At the end, they had a population of evolved C tier and Ns. They plucked out of the population the most fit one and played it back many, many times on the robot.
The 2 largest blobs in the ellipsoid bounding box are like pretty much right below the 2 large blobs in the sphere bounding box.
Yep. What does that mean? What does that tell us about what the robot is thinking or feeling?
For 40, like for the value of 47, it's like pretty much the same for both of them. It's
Yeah.
Using 48 to distinguish.
The robot's kind of showing off again, right? It says, actually, if you want me to distinguish between these things, I don't even need the 2 neurons you gave me. Just one will suffice. Thank you very much.
When it comes to the fitness function, is there a reason they chose to go with like a bounded fitness function versus like is there like a reason that you do that?
Probably not. They could probably get away with not making it bounded, but I think probably just so you can think through the math, it's a little bit easier, I think. You could give it a go. Other observations?
What are the rectangles that are lying outside of both of the dashed?
What are the rectangles that are lying outside of C sub S and C sub D? What do they represent?
There seem to be other parts of the like options that occurred.
What's going on here? Let's pick this rectangle out here. What is this rectangle representing?
Is that like an incorrect categorization of an ellipsoid?
Exactly. We know that the robot is in the presence of an ellipsoid in this case because it's in black. In this figure, everything that's black is the robot's in the presence of an ellipsoid. Everything that's gray is the robot in the presence of a sphere. So the robot is in the presence of an ellipsoid, and it draws 47 and 48 do something out here. What does that mean? What happened in that case, that particular presentation of that rotated ellipsoid? What's the robot telling us?
It doesn't know what it is.
Doesn't know. The robot evolved, the CTRNN during evolution got A+, perfect score. We then exposed it to more situations that it had never seen. Most of the time it does the right thing. In one case, it doesn't know. We train an autonomous car to distinguish between a pedestrian right in front of it and a shadow right in front of it. The autonomous car does perfectly during training. Great. Let's let the autonomous car loose on the streets of San Francisco. What could possibly go wrong? This is what keeps anyone working in AI and robotics up at night. We do not yet know how to guarantee that something during training, or in our case, during evolution, when deployed in the real world, in which it's going to see situations it never saw during training or evolution, that it's always going to do the right thing. In this case, the robot doesn't know whether it's looking at a pedestrian or a shadow. We don't know what it's going to do given that uncertainty. What else can you tell me about this figure? What else is going on? I told you that whenever the robot is in the presence of the sphere, 47 and 48 always do exactly the same thing. That was a little bit of an approximation. That's clearly not what's going on. The robot is seeing the sphere many times, but doing slightly different things.
Yeah, there seems to be two clusters within, so it's like, it knows it's sphere, but it's like it's sphere A or sphere B.
Sphere A, sphere B, good choice of words. What do these two clusters correspond to? Why are there these two clusters?
Because of the two positions.
The two, position A and position B, right? So the robot is not completely able to collapse intra or within category differences. The sphere doesn't feel identical to the robot in all cases. It feels something slightly different when it's in the presence of an A, starting from position A, in the presence of the sphere, position A, sphere, position B. Even within these two clusters, the bounding boxes for the spheres don't completely overlap one another. That's actually because of a detail of the experiment that I haven't mentioned yet. Anyone guess what it is?
Does it have to do with like the size of the sphere, like how the fingers kind of curl around some of it and not others?
The sphere is always exactly the same size. Something's causing a slight diversity, slight difference in the robot's felt experience.
They changed the weight.
They didn't change the weight of the sphere. It's exactly the same sphere. They keep placing it identically under the robot's palm. How can the robot be having slightly different experiences?
Even though it's placed under his palm, could it be in a different place on the...
They could have placed it at slightly different positions under the palm. They didn't do any of this. They added a little bit of noise to the CTRNN. As values were flowing in from the sensors, they ran a random number generator, and they changed the numbers slightly coming in. And the same thing with the numbers going out to the motors. They added a little bit of noise, a little bit of randomness to those numbers. Why do you think they did that? It's a minor detail of this experiment, but worth mentioning.
Just to aid in evolution, because of randomness.
They could be trying to aid evolution so that the evolution has to deal with slightly different situations. That's definitely part of it.
Does it kind of like have the effect of normalizing so like some inputs don't become like way more valuable?
Not quite. They're doing all this work in simulation, but the hope is ultimately to run this on a real robot. I mentioned at the beginning of this course, Heraclitus reminded us 2,000 years ago, man never enters the same river twice, right? In the real world, nothing is ever identically the same, unless we're in the Matrix. We don't know, but assuming we're not, things are always slightly different in our experience. That's them sort of, the investigators being optimistic that someday this might be tried on a real robot. So they're just trying to make this a little bit more realistic. So far, so good? Okay. Let's keep going so we can finish up this lecture today. We just saw this case. This was the best evolved controller from the first of those three runs. This is the best evolved controller, the best evolved CTRNN from the second evolutionary run. This CTRNN also got a perfect score during evolution. What's going on in this case? They've drawn things a little bit differently in this case. My apologies on behalf of the investigators. Imagine C sub S drawn around these boxes, and imagine C sub D drawn around these boxes. The gray and the black do not overlap. That's good. That's what we want. It could, right? It hasn't magnified inter-category differences very well. The sphere and the ellipsoid feel very similar to the robot. This may be difficult to see from the back. Look at the ranges of the values on 47 and 48. They're really tiny. 47 and 48 are actually not changing in value very much during this last 5% of the robot's experience with the objects.
So is it not that it got, like, whatever it tells us that we got more accurate? Like, it was able to more accurately tell which was which?
Maybe. It's actually making these bounding boxes are actually, globally speaking, very, very small, right? For some reason, that seems to be helpful for the robot to keep these boxes from not overlapping. So there probably wasn't pressure to make the areas of these boxes large. Here's another case over here. Here's the second best CTRNN from the second evolutionary run, which also got a perfect score during evolution. There's also no overlap between these, but these boxes, again, are really, really close to one another.
This is an example of evolution being a satisficer, not an optimizer, where, you know, it did what it was told, it minimized overlap, but it didn't do the optimal thing, which would be to also, like, maximize distance maybe between the two.
Yes, this is an example of the evolutionary algorithm being a satisficer, not an optimizer. All you told me to do was not overlap these boxes, and I didn't. You never said anything in the fitness function about maximizing the distance between them. I'm doing exactly what you asked for and nothing else. Look at this one. This is the third best CTRNN from the second trial. What's going on in this case?
The sphere bounding box is really small.
The sphere bounding box is really, really small. It's really reducing intra-category differences. The sphere in A and B feel really, really similar to the robot. Okay, that's the last slide from this lecture. Before we switch mental gears and talk about locomotion, Cam was just saying, intuitively, maybe it makes sense to push these bounding boxes further away. So let's take 2 minutes and rewrite this fitness function in our head and then mentally simulate an evolutionary algorithm running with this altered fitness function. If we added a term to the fitness function that rewarded for maximum distance between the centers of the bounding box, what are we telling evolution? We're building in our bias or our opinions about what the difference between spheres and ellipsoids is. The investigators didn't do this. They didn't include this additional term that maximized distance between CS and CD.
Well, one issue with that is that it would not necessarily, like, the could have a huge bounding box. It could be like really far away, and that could be really big, and then you might not be minimizing inner category differences.
Maybe. Other ideas?
I suppose we're like suggesting that a sphere can roll a lot better than an ellipsoid, so that's why it would be able to figure out that the spheres can roll like a lot further away.
Getting closer. We're not necessarily telling the robot or the CTRNN that spheres are more rollable than ellipsoids, because it's up to the robot to decide what to do. It didn't in this experiment, but it could have easily grabbed the object and banged it up and down on the table a few times. I don't know whether that would reduce intra-category differences and exaggerate inter-category differences, but it's a perfectly valid. There's nothing in the fitness function that says you must roll the object. Other ideas?
If you tell the robot to do that, and because these are so subtly different, it probably would increase the rate that you might roll something along the wrong end and not be able to make a subtle distinction between the two. Like if you made them move pretty quickly away from each other.
One thing you mentioned is certainly true, which is the robot would no longer, it would not feel a subtle difference between these objects. Assuming a CTRNN could evolve to support that fitness function, that ellipsoid and sphere would feel very different to the robot for such a CTRNN.
Yeah, I was gonna say, like, if the end goal of not this experiment but just in general was to be able to categorize like a set of objects, it's probably pretty nice that a sphere and ellipsoid are in the same like category versus like a triangle or like a prism.
Okay, you've anticipated my next question, so I'm going to more or less repeat verbatim what you said. Let's imagine we rerun this experiment, and now we expose the robot during evolution to ellipsoids, spheres, and cubes. Let's not change anything about the experiment except, well, we've changed the experiment by adding cubes. Change the fitness function. How do we want the robot to distinguish between ellipsoids, spheres, and cubes? How do we modify the fitness function? Just high level, we don't even need any math. What's the intuition?
Determine if it's like a cube or an ellipsoid / sphere first, and then determine if it's, based on what tree it takes, it's either a cube or it's use this fitness function.
Okay, we could design a fitness function that causes the robot to categorize hierarchically. Figure out, first of all, whether you're in the presence of a sphere / ellipsoid or a cube. And if you decide you're in the presence of a sphere / ellipsoid, tell me which of those two it is. Could go that way. If I were to ask you, and you can tell me with language, luckily, which of those three objects, ellipsoid, sphere, and cube, is different from the more different from the other two? Which one doesn't belong? What would you tell me? Presumably. Are we all in agreement? It's the cube, right? There's something about humans that we actually agree in this case. We are aligned in the new language of AI. We have value alignment in that problem. So we probably want to teach this robot or evolve this robot to feel that ellipsoids and spheres are more similar to one another than either is to a cube. How do we alter the fitness function for that? What do we want to see in these three bounding boxes we're going to draw for sphere, ellipsoid, and cube?
Well, the cube would be much farther away from the sphere.
We want them all to be mutually non-overlapping, but we would like the cube to be further away from the sphere or the ellipsoid. So coming back to something Cam mentioned a few minutes back is actually the distances between these boxes. We could manipulate this so that the robot learns semantic relationships, similarly to humans. We could end up making this robot more anthropomorphic. It not only looks like us, but it experiences the world like we do. If you, blindfolded, grasp ellipsoids and spheres, they're going to feel more similar than a cube does. Make sense? Okay. All right, we've got 10 minutes left, so let's pull out of active categorical perception and the minimal cognition experiments and dive into locomotion. Okay. We're only going to start to scratch the surface of this topic today. It is a long and fascinating topic. There are whole course series on biomechanics, so we're going to treat this at a very high level. One of my favorite books of all time is The Principles of Animal Locomotion, written by Alexander. And one of my lab members currently has this book, and I've forgotten who it is. One of those lab members is actually here today. If I had this book, I would have passed it around so you can all have a look. It's all good. I'll give you the Coles Notes of Principles of Animal Locomotion. I love this book because Alexander goes through in one book more or less every single way that Mother Nature has discovered to get animals from point A to point B. He starts at the beginning of the book with some of the basic physics we need to think about locomotion, goes into obviously the single building block every single animal uses to move. There is one cell type, more or less, we all use to move. It's the muscle cell. Okay, this has come up a few times, the energetics of locomotion. As you've probably noticed, your 3-link robot is not very energy efficient. It can, under the right conditions, bounce all over the place. Generally not a good way to get from point A to point B. Goes into all the different aspects of the physical body that affect your ability to move from point A to point B, and then goes into all the different ways Mother Nature has figured out to move animals from point A to point B, starting with some of the earliest and simplest cases like peristalsis. So the humble earthworm expands the front of its body, which ends up being an anchor where it presses against the inside walls of the earth that it's moving through. It contracts the back of its body, so the back of its body loses contact with the tunnel and causes the back of the body to contract forward. When it does, it relaxes and expands another part of its body. And as this wave of expansion moves from the front of the animal towards the back, the animal actually moves forward. This is peristalsis. We do not move with peristalsis, but you have peristalsis going on in you all the time. Where is it? Kind of here, a little bit here, more elsewhere. A little bit in the intestines. Throat. When you swallow anything, peristalsis pushes the food back. This little hack, this combination of shape deformation, changing shape, and geometry, and how things change over time, this little phenomenon is super helpful, and Mother Nature discovered it a very long time ago, and she's copy and pasted and adapted that mechanism into all sorts of animals all over the place. Walking, running, and hopping, this is where we as humans tend to feel more comfortable. Climbing and jumping. This particular primate, the gibbon, is very good at brachiation, swinging from branch to branch. Homo sapiens sapiens, we're not so good at it. You can spend years training and you can get better at it, but nowhere near as good as the gibbon. I highly recommend getting on YouTube and Googling videos of gibbons brachiating. It's fantastic. Crawling and burrowing, something humans don't tend to do very much. Gliding and soaring, we need machines for this. Hovering, powered forward flight, moving on the surface of water, swimming with oars and hydrofoils, swimming by undulation, swimming by jet propulsion. Who swims by jet propulsion? Octopus, the cephalopods, and so on, right? Incredible diversity in the ways in which Mother Nature has found to get animals from point A to point B. I want to back up for a moment. This is going to anchor our discussion for next time. All of this diversity is Mother Nature trying to strike different kinds of balances between 4 antagonistic forces that are at work the moment an animal starts to move from point A to point B. There is no optimal way to move from A to B. There are just different trade-offs that you can strike in the way that you do it. These trade-offs are summarized as displacement, robustness, energy, and stability. An animal that evolves to maximize displacement and ignore these other three desiderata, how is that animal moving? Regardless of whether it's on land, sea, or air.
It's like sprinting.
It's sprinting, right? So the minute you sprint, you're choosing a particular way to get from point A to point B. You're striking a pretty extreme trade-off. An animal that values robustness over the other three, robust to what, do you think? It's not mentioned here.
Like forms movement, like not just straight forward and backwards, but like in other planes.
Could be like the directions in which you move. Usually when robustness is mentioned during the biomechanics of motion, it's robustness to the different environments you might move through. If you're moving over land, it's differences in friction and structure of the ground over which you're moving. Are you moving over ice? Are you moving over a boulder field? Are you moving through a field of wheat? Are you moving through... Can you be robust? Can you continue moving in the way that you normally move under all those different environments? Again, as humans, we can sort of tune how we move. How do you choose to move so that you maximize robustness? It certainly ain't by sprinting. Not a good solution. You sacrifice robustness the moment you try and maximize displacement. I don't know how icy it is out there today.
You take little baby steps and kind of, that.
This actually works pretty well for pretty much most environments you can imagine, right? Walking over ice, walking over thin ice. Good strategy. What about animals or humans that prioritize energy over the rest? Walking. We evolved bipedal locomotion. We, Homo sapiens sapiens, are the master, the uncontested master of moving where we maximize energy and don't care about the rest. I think I mentioned this already. There's a theory out there about early hominids that one of the things that made us successful is that we hunted in packs, and we did it by just walking. Get a bunch of your friends, walk, have the ones on the outer side walk a little bit faster, and if you keep doing this all day, you can actually bring down some of the megafauna in North Africa. It's possible. I don't recommend it, but it's possible. We can sweat, we're very energy efficient. We basically counter our energy against the other strategies of megafauna on the plains of Africa, which is they tend to maximize displacement, right? Run away quickly. What about stability? We are terrible at this one. How many of you have seen somebody slip on the ice this winter, right? We're not so good at this one. The minute we focused on this one with bipedal locomotion, we really gave up on this one. My 2-year-old at home is still struggling with this one. Which animals are really good at this one and terrible at the other three?
Four-legged animals.
Four-legged animals? Actually, they're better than us. Everybody's better than us. But even four-legged animals, not so good. You ever seen deer jump on the road, icy road? They also wipe out. They're not great.
Something like a snake doesn't have legs to balance on.
Absolutely, right? Worms, snakes, reptiles, excellent at stability for the simple reason they can't fall down. Why would you ever evolve away from snake-like or reptilian locomotion? If you've got 4 legs splayed out horizontally, like the reptiles do, and you can never fall over, why evolve into us? Why evolve into mammals that move away from this strategy? No pun intended.
You can move faster and traverse like different grounds, and we can go up, or we can go vertically a lot better than.
True, right. So as hominids, as primates, we can climb. Although reptiles are pretty good at climbing too. Snakes, you wouldn't think it, but they're also pretty good.
Does it end up being more beneficial to have a better energy relation than being more stable, like in an evolutionary sense?
If you think about it, right, you can try this. Don't do it with anyone around, but you can get down on your belly and crawl around. It's exhausting, right? You're literally dragging your body along the ground. Friction is draining your energy. It's extremely energy inefficient to move in this way. There is no optimal way to move. Every way of moving is just a trade-off. Okay, I think that's a good place to pause for today. You have a quiz due tonight. Undergrads are working on A7. Grads, you're working on D2. See you here in class on Thursday.